So before I start, you mentioned already QMath, and this is sort of my kind of research home, where together with my colleagues, Jana Philipp Soloway-Berg von der Durhus, Laura Manczynska, Albert Werner, and Daniel Miles and Stanisław Franco, and Søren Fournet, of course, he used to be here, have a research environment for everything theoretical about quantum information science, both from description of quantum systems to quantum information theory, and we sometimes go on a retreat. And so I wanted to show you this picture from our last retreat. So we're about 50 people now, and it's a great fun environment. If you're in Copenhagen, feel free to pass by for our quantum lunches. We're always on Wednesday lunchtime. Actually, I guess today it's just happened already. So I want to talk to you today about fault-tolerant quantum computing, and this is work that I started some years ago with my then postdoc Alexander Müller-Hermes, and we wanted to understand if you can use faulty machines to actually do optimal quantum coding. So that's how we started, and then I have been continuing this research line with my current postdoc, Ashutosh Goswami, in collaboration with Omar Fauzi from Lyon, to understand more generally, to build a new toolbox for fault-tolerant quantum computing. And that's what I want to tell you about. All right. So here's an overview of my talk. So I first want to tell you about what is fault-tolerant quantum computing. Then I want to tell you about this maybe new vision for it, which is quantum computers that take a quantum input and a quantum output. I call fault-tolerant quantum I/O. And then I want to give you a few applications, both to traditional fault-tolerant quantum computing, to quantum communication, etc. But let's first kind of like do a slow start into the field. What is fault-tolerant quantum computing? And you know, before we talk about quantum computing, let's first talk about quantum computing before we make it more complicated. So here is probably what you've all heard about. That's the famous Shor's factoring algorithm. And it works like that. You get a big number, or you get some number, and the task is to output the factors, factorization. So 15 goes into 5 times 3. And this is my one for the audience. 781 goes into... See if someone answers. Someone always. Sorry? It's 71 times 11. And then this one I don't expect you to do. So then we have search. So here's a phone number. It's a typical as the phone book problem, right? I give you a phone number, which is the entry to it. That's actually my number. This one you can decipher. It's from France. It's the institution of my collaborator Omar Fauzi. It's Ernest Lyon. And then this one here, I don't know. It's maybe Peter Shor's number. All right. And the last problem that is maybe on the back of many people back of mind of many people when they think about quantum computing, that's a problem in chemistry. And the algorithm, there's a quantum phase estimation algorithm. And here the question is, I'm kind of like given 2 molecules, so they're nuclei, and I want to know what is the interaction energy, what is the binding energy for them. And you know, maybe I have independence of a distance, and I get an energy profile like this. What do all of these things have in common? Namely, all of the things have in common actually that the input to the problem is. So I'm struggling with my laser pointer here. That all have in common that the input to my problem is actually classical. So it's like if you can encode it in a bit string, and the output is also in a bit string. So in some sense, the way here of thinking about quantum algorithms is think about you have a problem and you're building a quantum machine that solves your traditional classical problem. And I want to get us a bit away from that later. But what's important here also is that the assumption of a noiseless quantum computer is actually unrealistic. So what happens in practice is that you will get errors during the execution of the quantum computation, and if that happens, you cannot be sure anymore what the output is, and it happens in all of those. And what we my Klaus Melmer joke. And this, of course, might also lead to completely wrong conclusions. So in order to run a quantum computation, we need to make the quantum algorithms robust so that we can run them on noisy hardware. And that is the topic of fault-tolerant quantum computation. In order to understand how this is done, we have to understand how does the quantum algorithm look like. And the typical model is that you write it in terms of elementary operations. So you pick a universal gate set, typically given by your quantum computer. Here is an example of such a gate set. It has an X gate, a Pauli X operator, so you have single qubit gates, Y or Z. It has a C0 gate, say an action gate. And then actually it's useful, it's maybe a little bit unexpected, but it's useful to also talk about say the identity gate, like the gate that does nothing. It's also good to talk about the gate that takes nothing in and it prepares the quantum state 0, or takes nothing in, prepares the quantum state 1, or also does a measurement or a partial trace. So think of the gate set not just as a bunch of unitaries, but also as these preparation and measurement problems. So then a circuit will always be, like Shor's algorithm, will always be given in terms of these gates. And then, of course, if you have a physical implementation, the quantum bits are illustrated with are kind of like the wires, right? And the gates here, this is a 2-qubit gate or 1-qubit gate. So the qubits are implemented in maybe ions or atoms, and the gates correspond to laser pulses. If you have superconducting qubits or spin qubits, the gates are maybe microwave pulses. If you have photonic qubits, the gates are beam splitters, phase shifters, or maybe some nonlinear elements. The gates typically in current hardware, they have maybe an error rate of percentage level to sub-percentage level, maybe 10 to the minus 2 to 10 to the minus 4. And this is due to different effects of a type of error. One could be interaction with environment. That's sort of the typical one. Then you, through that, you get corresponding channels, error channels like amplitude damping or dephasing, but there could also be some calibration errors. So you do an imprecise implementation of the gate you want to do, maybe an over-rotation, or also things could leak into additional higher lying levels. So then when people noticed this, and Peter Shor had come up with this algorithm, they said to Peter Shor, well, Peter, it's not going to work. Your algorithm is never going to run. And then Peter Shor kind of went back to his desk and said, let me invent error correction. So he invented quantum error correction. And quantum error correction starts with normal error correction. And the normal error correction is so the repetition code. So for instance, I can take a 0 and code it in 0, 0, 0. If or in the 1 I encode it in 1, 1, 1, so I just repeat it. Then if one error happens, say I'm having a bit flip error here on the second bit, then it goes to 0, 1, 0 or 1, 0, 1. Then if I do a majority decoder, so I just count how many zeros and how many ones are there, I can still successfully decode it. And so error correction is really good. This repetition code is good in suppressing the noise, right? So then I only get noise only when I have 2 errors, which then would probability squared. So I can suppress from error probability delta to delta square with such a technique. So Peter Shor started looking at that repetition code, and he said, well, quantum bits, they have both bit flip errors and they have phase flip errors. So he built a code that combines them, so basically does the error correction twice, once corrects one error and then the other error. So you can now stare a little bit at it. I will not explain it much. But what you see here is that, so that's why it's a 9-qubit code. Here's the encoding circuit for it. You start with the all zero and you want to say encode into the zero code word. Then you see that you have a bunch of controlled NOT gates here. And then you have a Hadamard gate, a bunch of further controlled NOT gates. And then at that layer here, you then have your encoded state. And then afterwards, maybe what happens is you get an error here. And if you have only one error, then actually the error correction just before, just like in the classical case, the error correction procedure is able to correct this error. So that's very nice. So in some sense, you might think this solves the problem. But what happens in quantum computing is actually a little bit worse than what I've displayed here. What happens in quantum computing is that the error might happen here during the computation. Okay, so the Hadamard gate might be thrown out. And then the error can spread. But Shor's error correcting code can only correct for one error. But now the error from the Hadamard gate spread and actually generated 3 errors. So the error correction will actually fail. And what do we do about this? Well, we have to kind of make sure that we design our code such that the errors don't spread, in some sense. And this is the topic that then moves from error correction to what is called fault-tolerant quantum computing. Okay, so that's the difference between error correction is when errors happen in storage, and fault-tolerant quantum computing is when error happens during computation. That is the distinction. So how does that work? So every gate will kind of be replaced by, so every qubit will be replaced by say here 7 qubits. Every gate will be replaced by some gate, something that acts on the 7 qubits. And so the circuit will be modified into some bigger circuit where that is constructed in some way. And I said 7 because one of the popular codes that we also use in some of our work is the Steen code, which is 7-qubit Steen code. Now, you do this once, it suppresses the errors once. You can, yeah, here's actually another code. It's a 11-qubit code, which is actually a little bit better. It corrects 2 errors, not only 1 error. So it's actually more useful, but it doesn't really matter. Just to show you that that there's different codes and you can use them. They have different properties. But what you can do is, so when you do it once, it basically reduces the error from delta to delta square. Maybe there's some constant in front, but let's not worry about it. And then you do it once more, then you square the error again. So actually, as each time you do this encoding, you can kind of like layer this. The number of qubits goes up, so the number of qubits increases exponentially, but actually the gate quality improves doubly exponentially. So things look good when you do this. And okay, so there was another slide on this. You can also do this for the decoding. Yeah, the concatenated. Just introduce basically this triangle for encoding and decoding with this slide. So how do we get Shor's algorithm now fault tolerant? We start with our big integer as an input. We encode it into the logical subspace, or like I showed you with the Shor construction before. Then we have done this. Every gate was replaced by these encoded gates. So we do this encoded circuit. Then we decode, and then we get hopefully our output. So the input and the output here are classical, like in Shor. And you can think of this classical bit as already kind of assumed to be stable. And so in some sense, like actually the bits in my computer, they're stable. They're not flipping just randomly. And so it's a reasonable assumption. So when errors now happen, the construction is designed in such a way that the errors do not spread. And you can think of this intuitively, that there will be errors happening, and then you start correcting them. Okay? So in between, you do error correction cycles. And these error correction cycles, they will correct some more errors. Because an error correction cycle itself is a circuit that you apply that again can have errors. It will also introduce errors. Okay, so you have to design the construction in such a way that the error correction you perform, it sucks out more errors than it introduces. Okay, and so it's kind of like you kind of like as if you cool the device. So the error correction removes entropy from the system, and this way you can keep the information stable and then decode again. So this is kind of like the high-level view on fault-tolerant quantum computing. Are there any questions? It's a good moment. Yeah? And it's important, yeah. I think that's okay, no question? Was so clear? Okay. I guess it's recorded. Anyway, so there's different error models. We could talk about this now, but maybe we skip it. A good way of thinking about errors is happening probabilistically. So it's probably like at every place, at every location in the circuit, so every gate, you keep it with probability 1 minus delta, and probability delta, you throw it out and you replace it by something else. It's one way of thinking about errors. There are different ways, and this makes the subject rather kind of like, let's say, involved, but maybe it's a discussion not for the talk now. I think I'll just skip that. Yeah. Here is now the formal statement that it's from a paper from Matthias Christandl, Preskill. There are other works by Ben Orr and Aronov and Kitaev before that. But the famous threshold theorem for quantum computing is the following. So on the right-hand side here, I have the circuit, like let's say the Shor's algorithm that I want to implement on a noiseless machine, right? And so what I actually do on my noisy machine, I implement this encoded left-hand circuit. Then the famous threshold theorem says that these two things are the same. And the precise statement is that there is a threshold for the gate error, delta 0, such that if your actual gate error is below that, then the probability that this left-hand side here is equal to the right-hand side, so meaning you can simulate the right-hand side on a noisy machine. And K level is kind of like the level of concatenation that I showed you. How often do we need to concatenate the code? How often do you need to do this procedure? So the probability that the output at the unencoded, so that's your desired thing, that the output is not equal to what you actually do on the machine, say you encoded K levels and with the delta noisy machine, that they're not equal, that's bounded by the size of the circuit times some number, okay? This is, now I wrote it down in this generality, but you think of this delta 0 as like, I don't know, a percentage, 1%. Then if your machine has delta, say 0.5%, then actually delta divided by delta 0 is a half, okay? Then it's a half to the 2 to the k. So that's a very small number. If you choose k, even order log of the number of gates. So actually it's a rather small overhead. And so that's how this kind of works. So with this theorem, it guarantees you that on a noisy machine, it doesn't destroy the complexity of Shor's algorithm. So if the number of gates is polynomial in the input size, so the length of the number of digits of your integer, then after you've done this manipulation with like putting on a noisy machine, it's still polynomial size. Okay, so life is good. So this is really the cornerstone. So how many of you are experimentalists? trying to build a quantum computer. And this is the reason why we believe you can build a quantum computer. Okay, so I think this is really the cornerstone theorem of the community. If we don't have that, you know, maybe we should spend our efforts somewhere else. But we have it. Very good. So yeah, this is So the important thing is, now I'm coming to the top of my talk. This theorem works for classical input-output. Okay, so it's like the short type of thing. I have a integer input and I have a thing output. Okay, so but what if? What if your device needs to interact with some other box, doesn't really know what to do? What if I have a computation, but my computer is too small? I need to distribute the computation onto several machines. Here are 3 different types of machines. There is an atom machine, there is a superconducting qubit machine, and these are quantum dot machine. Or what if I want to do quantum communicate between 2 quantum computers over longer distances? In all of those situations, we need to receive quantum information. And if we need to receive quantum information, we could either say like, hey, just give it to me in my favorite quantum error correcting code, right? I specify, I like the, you know, whatever, I like the 7-qubit Stein code. Please deliver the quantum information to me 3 times concatenated in the 7-qubit Stein code, right? But that clearly puts the burden on the sender. If the sender's got a machine that doesn't like the Stein code, but it has like, I don't know, a surface code, like 100 by 100 surface code, then I'll have a hard time receiving that, or they have a hard time sending that to me. Or I need to send the information. Well, that puts the burden on the receiver. So somehow, if quantum computers are interacting in a quantum way with other quantum computers, someone needs to solve this problem of like quantum input-output. How do I make that fault-tolerant? Okay, so and the theorem before doesn't cover that because it only had classical input, classical output. Here is a statement we can make about the situation. And that's a statement in the situation where my quantum computation actually still has a classical input, actually like no input, but it's like the same as having classical input, and it's just preparing a quantum state. Okay, so on the other side is a quantum output. And so what do? I could just follow my strategy from before, right? I could like say, hey, let me encode the 0 into the logical subspace. Let me take this quantum circuit that produces that quantum state. Let me encode it in the strategy just explained, and then I'm done, right? But the problem is that here this was like an n-qubit state. If every qubit is now encoded in a 7-qubit Stein code, then this here is 7 times n qubits. Okay. So I cannot just do that strategy. I have to decode. Natural is to decode this quantum information here again, and then basically what happens is I have a circuit that if there's no noise, right? If there's no noise, the left-hand side will actually be equal to the right-hand side. Maybe I even have this equal. It actually will be equal, not even approximately equal. Okay. If there's no noise on the left-hand side is actually equal to the right-hand side. The problem occurs. So and it was designed such that when the errors happen, actually the construction was such that the errors do not spread throughout this, do not spread through the circuit. So the problem is only that you see at the very end of this procedure, here at the very end of the procedure on the right, what can happen is that I don't end in this classically stable information. I end with qubits. So what can happen is that the last operation here, the last thing touching the qubit will have an error. And if that happens, like maybe here, you can see it, the last one you could touch it, then actually there will be an error here. So when I have this quantum output, actually I cannot expect to I cannot expect to get the exact state, because I cannot avoid, with any procedure I'm designing, I will have a last layer of gates here, and they will potentially introduce an error. That means that the best I can hope for is that I get only a very small fraction of the qubits will be affected by error. And in fact, this is what we can show. So the theorem here is basically telling you it's optimal, and it's telling you that if you want to prepare a quantum state, you can do it if you're happy to accept a small layer of noise at the very end on top of it. Okay? And this is actually already quite good, and in many cases is sufficient. So you cannot do better, because any procedure you come up with, it will have a last layer of gates that might have errors, but it's achievable. And so it's one of our statements. We have a different statement, a similar statement for quantum input and classical output, which will be like a measurement, and also statements for where both classical input and output are, where both are available, but then they get a little bit more complicated. So I just wanted to kind of present to you the simple one. Do you have any questions? Yeah. Yes? When you have an arrow on here, you mean here? Well, because the information here is classical that you start with, actually this procedure, you can basically, this encoding thing is designed in such a way that you can make an error detection, and if you detect an error, you can just repeat it. And that's actually, it's a procedure already due to Shor, I think, to make this this gadget. But you see that if there's a quantum thing coming in, then you cannot do that. You cannot just repeat, because then the quantum information is gone. All right. Okay, I want to very quickly show you how we prove these things. Basically, I want to show to you that the left-hand side is equal to the right-hand side. Okay? So the way you do it is you insert the identity. So the identity is like, if I have, I have something in I have something in my code, I can decode and I encode again. And the yellow things are error syndromes, right? When I decode from my code, I get some positions that tell me where there have been the errors. And so if I have some code state with some errors on top, I decode, I learn where the errors are, and I get my decoded qubit, and then I insert the errors again, and that in total gives me the identity. So I can insert this identity into my circuit, and you see when I insert it here, it's actually kind of, there are no errors on it. There was just a mathematical procedure that I'm doing here. And then then what happens here, what you see here is that here I suddenly, if you just look up to that point, you see that this is an ideal decoder. So these green boxes here, they don't have any error. And because they don't have any error, actually already the theorem by Gottesman and others tell you that you get the perfect circuit there, plus some error syndrome. So you can kind of like box it into this level. And on the other hand, these guys here is like a perfect encoder followed by a noisy decoder. And this is possible to analyze. Yeah, so the error syndrome is basically just telling you where the errors in the circuit have been. And this effective circuit you can show, and this had been shown by a paper by the Horodetskys already earlier, that this here is basically the identity plus order delta noise. And then you see that you essentially have prepared the perfect, at that point here, you have prepared the perfect state plus a layer of noise. Okay, and then you can, and then you essentially are there already at the statement. that you have the circuit plus the layer of noise. So this is sort of like a box analysis for how to prove such a statement. All right. So I want to give you in the last minutes a couple of applications of the result, and maybe give you an outlook as well. Okay, so one of the applications, it was sort of like it's kind of like traditionally the community that I'm coming from, that's the quantum communication community. So what happens in quantum communication? In general, in communication, we take the paradigm that Claude Shannon started in the 1940s. You have some input, and you encode the input, and then you send the. Now you have to be aware that there's like the word code I'm using now in a different way. Okay, before it was the code for the error correction. Okay, it's like a different code from the communication code that I'm using now to going on the channel. Okay, so the encoder is now something that, you can think of the number of input bits now, I don't know, 10,000, and then I have my encoder that takes these, makes a code for 10,000 bits and sends it to the channel. Then there's a decoder and then the output. So M input bits, just some notation, N channel uses, and there is a famous capacity formula, capacity definition. I should use this really. So the capacity of a channel is given by the ratio of M divided by N. Okay, well, so how many bits do I push to N uses of the channel? And then I want that the probability that the input is not equal to the output, I want that to be bounded by some epsilon that I have chosen. Think of epsilon being very small, like 10 to the minus 8, 10 to the minus 15 or something like that. And but think of it as fixed. Then you take the block length to be large, okay? So epsilon is fixed, but the block length goes large. But you really think of the epsilon so small that later you can kind of, doesn't matter. It's like take the epsilon to 0, okay? It's very important in which order you have these quantifiers. Okay, first you have to fix the epsilon, and then you have to take the block length large. Okay, so, and Claude Shannon, he proved that this has a nice formula, okay? Actually, for the talk, it doesn't matter that it has a nice formula. This has Shannon entropies in there. It's a very nice formula, but we don't care, I'm afraid. So this was sort of the state from 1940 to 1960. And in the 1960s, Alexander Olevo, he noticed that, hey, if I have a glass fiber, this model here of a normal channel and bits and so on is not sufficient anymore. So he said, these are now quantum, okay? So let's take the channel to be a quantum channel, maybe something over which I can transmit single photons that are not described as bits anymore. Then the encoder and decoder, they are now quantum. But for simplicity, really just for the talk, we can keep the M bits classical. Okay, so we still want to transmit classical information across. So we transmit M bits over the channel, and that we can also do qubits, but let's keep it at bits. So the capacity formula, it's the same actually, right? Don't change anything. This is called the classical capacity of a quantum channel. It has a similar formula called the HSW theorem, but also the formula doesn't matter so much. And what you should at this point, and this is a phenomenon entropy instead of the Shannon entropy, but never mind. But the observation is that this assumption here of a noiseless encoder and decoder, which I can design, is unrealistic. And you see that it falls outside the paradigm of the standard quantum computing of making it fault-tolerant, because the encoder, even though it takes a classical input, it has to prepare a quantum state for the quantum channel. Likewise, the decoder has to take in a quantum state. So it's quantum input here, and here, this guy, the encoder, has a quantum output, right? So that's my state preparation device from the theorem from before. And so if this guy gets noisy, right, then actually entirely new problems appear. And the first question you might ask, can I communicate at all? And the answer is yes in this particular scenario. The next more advanced, and it's not so hard to see that the answer is yes, but is it still at the similar rate as before, right? So, you know, I have this capacity formula. Is it still like a similar formula, or is it like half of that or something? And we show it's continuous, so it's still yeah. When the gate error goes to 0, you want to approach the original one, and this is sort of the statement that we have in our first paper. So you basically want to, and this is kind of our threshold theorem. So you have the same formula as before. Now you go over encoder decoder pairs. And you want to know how closely is it related to this, to when the machine is noisy. And right, so this is like the noisy machine. You run it on a noisy machine, or you run it on a noiseless machine. You want to relate those two, right? You want to know if the capacity on the noisy machine is like close to the capacity on the noiseless machine. And the important thing to notice here is actually that the noise is constant, okay? So the delta is constant in this whole problem. So the channel capacity now has two parameters, namely the channel and the noise. So here's our theorem. So there is a threshold, blah, blah, blah. And the capacity at delta noise is actually, of course, it's smaller than the capacity at zero noise, but not much smaller. Minus a little fudge factor, and the fudge factor goes to 0 as delta goes to 0. So establishing thereby that the traditional model for quantum communication is actually okay. Okay, so life is good, we're fine. Okay, we can still do communication at the optimal rate, even though the devices are noisy. All right. Yeah, we also did some other stuff. Yeah. So I guess you know, here's kind of like how you use it. You basically take the left-hand side up there, right? And now here you remember the state preparation statement that I had. So you can just replace it by the perfect one plus a layer of noise, and on the other side as well. I didn't show you that. And then you show that this one with this additional layer of noise has a similar capacity to the one without these additional layers of noise. So it's kind of like two-step process. Yeah. Okay. All right. So that's our theorem. Yeah, there's one application. I hope it kind of like motivated why we're doing this. We can also, another application, maybe it's more unexpected, is that within a quantum computation, there is subroutines happening, okay? And the subroutine may consist of, hey, you should prepare that in such and such state. And this is particularly the case, people talk a lot about Clifford plus T, or, you know, Clifford operations are cheap, and then you have some other operations, and you want to, like T-gates, magic states, I don't know what, and you want to use them you want to prepare some magic states, and then you want to inject them via gate teleportation. This is sort of like I'm not sure if you're familiar with this talk, but so basically a subroutine in quantum computing is to prepare quantum states. And that is, of course, what we're good at. So we want to use them in this context. And that is what we can do. And what we managed to do is, okay, so I think I'm a little bit out of time. I will not tell you how to do that. But essentially, what I want to tell you is that our fault-tolerant, our statements, they work in a very general noise model. And in this very general noise model, we can also do coherent noise. So also if you have these over rotations, and then we can say like, hey, the results that were there before with the state preparation, now with our general noise model, they still work. And we can still prove now a particular result, namely a very efficient fault-tolerant architecture with only a constant overhead. That means that like if you don't need, if you're going from the normal machine to the fault-tolerant machine, you don't need more space. You keep basically the space the same, so the number of qubits stays roughly the same. Right. So, summary. So what I hope I transmitted is that we have a new paradigm for fault-tolerant quantum computing, fault-tolerant quantum input-output. This is actually a picture from an experiment of Eugene Polsik and Jean-Baptiste Beguin in our Quantum for Life Center at this is at the Niels Bohr Institute. It's a neutral atom array, which you can see here. It's held there, and I hope I convinced you of the relevance for quantum computation, in particular that it establishes that this traditional model for quantum computing, for quantum communication is okay, and it also gives constructions. I think what is cool about it as well is that we're trying to build this toolbox, which will be relevant more generally when we are connecting different processors, different quantum processors together, and we want to let them communicate, interface with each other, and not to have to do a analysis one by one. And with that, I want to thank you for your attention, and we do have, we also can hop. So, anyway.
Very nice.
Already stopped hopping. Thank you for your attention.
Let's thank the speaker. So it's time for questions now. So there's a question here. Yeah, go ahead.
Thank you so much for the super interesting talk, and I love how you sort of very clearly explained all of the steps in fault-tolerant computation. I wondered about the proofs that you showed at the end. Are they? And you talked about the scheme that you use in your group of the grouping the qubits into 7 and then doing the 3-stage concatenation for the encoding and decoding. Are those proofs regarding the? Are they generalizable to all different ways of constructing the qubits together? And all different ways of constructing encoders and decoders, or are they specific to the particular scheme that you talked about there? Because I guess people are working on other schemes or researching other schemes.
Yes, this is a very good question. So the construction that we're having for the particular result I show you, where for concatenated codes with certain properties, so like they actually need to be this distance 5 at least, and then you can and then we can apply the framework to do it. Actually, 7-qubit scene code will not be good enough for that, but the for what I showed you, it's the at least distance 5. Then you can apply this Kitaya framework in which you're working on fault tolerance to do it. We're using this to establish kind of like these fundamental results. So when you you cannot just swap it out against, but there is families of codes that satisfy these properties. I think that's maybe fair to say. The second result that second application I flashed had something to do with quantum LDPC codes, and there we also used quantum LDPC codes for doing things. But it's in general, it's a rather involved subject of proving fault-tolerant results. So very often you need to kind of like, there will be no result that will hold like universally. So you will always need to make choices of your construction, because it's a constructive enterprise. Yeah, that answered you.
Thank you. More questions? Thomas.
Also, thank you very much for an interesting talk. Now you talked about one of the use cases for fault-tolerant I/O was to connect different architectures for quantum computers, so you can kind of like keep the calculation going on another processor. Do you have any kind of like a algorithmic example where it would be beneficial to go from kind of like one architecture to another, or is this still an open question?
Yeah, no, no, I don't have it. No, it's more, I'm thinking of it more in the way of you wanting to carry out a large computation and not having enough memory. And maybe then what you need to do is you need to kind of like distribute your computation, and that'll require you to shuffle, to put some information here and some information there, and like shuffle things around. We have not directly made like a direct blueprint application of this type, but certainly that's the way, that's the vision to go. And as an example, you can see you can see this the communication paradigm, where you kind of don't want to where you do some computation here, then you send the information, and then you do a computation here. So that's maybe an example of a rudimentary example of how to envision this. And you can of course also concatenate this with like maybe more computers, etc. Yeah. So yeah, but it's usually like the tools are there to, or at least my vision is to build tools in order to overcome the restrictions that we will have in building quantum computers.
But to elaborate on that, maybe one could have one quantum computer where you have storage, like long storage of qubits, and another one that's good at computation, and maybe you want to exchange between these two.
Yeah, maybe you want to exchange between those two. Yes, that could be another example here.
There's a question over there.
Thanks. My understanding is why quantum encoding and decoding could be more complex and tricky than the classical ones, because encoding and decoding also involves quantum circuit, and so the algorithm itself is actually not deterministic compared with the classical one. So I see also you have like quantum LDPC code. I'm wondering what kind of features make a good code for the quantum computing, quantum encoding, quantum decoding stuff.
What makes it a good code for the fault-tolerant architecture, or a good code for a good communication code? Which one do you mean?
Fault-tolerant.
Yeah. Okay. So as so I think it's this for the fault tolerance. It's this idea that the errors don't propagate too fast. Okay, so within your architecture, you don't want the errors to spread. You remember my example of like the Hadamard being thrown out, and then the errors spreading through the CNOT gates to 3 qubits. So you want to kind of like avoid this spread of the information. So that is certainly what is a good argument for building these codes. And so that's the property that you want, and there is of course some the mathematical ramifications are then that the operators that you have to measure in your code, that they don't touch too many qubits. Okay, so if you have operators that touch too many qubits, things will spread. So you want to keep kind of like information there somehow from they should only touch few qubits, and then it will not spread too fast. So that's maybe the mathematical.
Thanks for the talk. I also have a question regarding this encoding of a circuit to make it fault tolerant. Is there a straightforward, implementations of such codes, or does it become computationally very complex to find such a fault-tolerant circuit? So is that a bottleneck? Is my kind of my question to find.
Is it a bottleneck to make constructions?
Yes.
Certainly, this is a big industry. So making constructions, understanding how high the threshold is, this is a large effort of the community. The research community, a large effort in figuring out which codes to use for which architecture. So, for instance, these atom machines have the possibility to use completely different architectures than on, say, 2D planar layouts, like superconducting qubit layouts, you know, people will focus on surface codes. For the others, now people are talking about quantum LTPC codes to do those. So the platform comes with certain limitations on the codes, and then the codes need to have certain properties. And then you want to square this, right? You want to figure out, like, okay, which properties do I want? How do I, you know, yes. So this is quite some effort in the community, really large part of the community. And many different constructions, very, you know, you can also approach this field now. Of course, the natural question is also like, okay, so you gave these deltas, how big are these delta thresholds? And it's like, okay, that comes out from these like constructions. I don't know what it is, maybe 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, something like that. Maybe worse than that. If certain simulations of surface codes have shown that you can do up to percentage level. Okay, so you can do in certain architecture, you can get away with percentages, and so on. So there is it's a community here. It's a community effort to get this worked out. Also, like maybe I should add, and maybe I didn't put enough weight on this. The codes need to have the property that you can execute the gates in them, right? So these fault-tolerant codes, you need to be able to not only error correct, which I was kind of emphasizing, but you need to execute gates on them. And executing those gates is a huge constraint on the code, on the type of code you want to do. And yeah.
There's still time for a question. While you think about it, oh, is there a question here?
Following your comments, would that mean that if the code is symmetric, it will make the circuit design easier for computation?
Yeah, that I don't know. I mean, depends what means by symmetric. I think most of the designs that you can sort of like write out by hand, like for instance these surface code designs, they are basically, many of these surface code designs, they actually come from condensed matter theory models. So where you think of a grid with where the stabilizers are like plaquette operators, and so like plaquette operators, a bit like generalizations of, if you're familiar with the Ising model. So generalizations or quantum versions of like the Ising model, they lie behind many of the codes, many of the ideas of codes, topological codes coming out of that. So those have natural symmetries in them just in order to be able to construct them. But that doesn't mean that you can't have constructions. There's also another area that would be taking classical codes and building quantum codes out of pairs of classical codes. It's another type of construction, and so on. So there's not necessarily symmetry, but yeah, certainly helpful.
Well, I have a question myself, Matthias. So I would like to explore a bit the interface between this quantum computing and classical computing. So, and there are two instances I could think of, and the question is, does it make sense? So one is you could do error mitigation calculations classically. So you get the results, they are not precise, but you do some analysis afterwards. So that would be one thing. And the other thing, I'm not sure, but maybe part of the decoding that you have to do at the end could also be done in the classical realm. And the question is, could such things help in reducing the cost of quantum error correction?
Certainly, the quantum error correction already has a large classical component, right? So because you measure the syndromes, and then you have to compute the correction, which correction to perform. It's actually one of the hard parts of this whole error correction, is that you need to figure out, you get all the syndromes, you kind of know where the errors happen, how do I correct them, okay? And this is certainly one enterprise where already this enters. Now the topic of error mitigation, that is something that you, so error mitigation, for the people not so familiar with it, is sort of what people usually call the step before you do full-blown error correction. So I was kind of doing full-blown error correction, like as much as I can the whole time. But if I, for some reason, don't have this ability or don't want to give myself the ability, then I can try to kind of like mitigate the error. Like, And there, yeah, so by, say, repeating the circuit and do some advanced data analysis on it. Fundamentally, this will still have an exponential overhead. So you cannot somehow get around using error correction in fault-tolerant quantum computing. We know that. But so you will have this exponential overhead, but of course that doesn't mean that you cannot do something intermediate. That, you know, and I think this is exactly what people are exploring now, right? So like we had this regime where we can do some error mitigation and maybe we can do some correction, but maybe we don't have enough space or we cannot do enough full-blown. And that's a huge area where, you know, yes, you could do optimization, additional data analysis, etc. Maybe a good example is phase estimation, where a lot of the push has been to reduce the number of qubits and drive as much onto the classical data analysis afterwards. So yeah, it's a huge intermediate zone. In some sense, you can say like, hey, I went onto kind of like the future project, right? Like of fault-tolerant quantum computing. I showed you one application at the end, which is this constant overhead on like trying to get the fault-tolerant computer to be as small as possible after all. But there is, of course, a huge area from now to having the first codes that will be very interesting interplay with classical.